Hello, Matt here from chemistrystudent.com. In this video, we're going to look at the nucleophilic substitution reaction between a halogenalkane and a cyanide ion, forming a nitrile. We're going to talk about why and how the reaction happens, outline the reaction mechanism, and look at why this reaction is very useful in organic chemistry. Other reactions and mechanisms of halogenoalkanes have been covered in separate videos. Check the links in the description below. Before we talk in detail about the reaction, there are a few essential ideas you need to be comfortable with. Halogenoalkanes, also called haloalkanes, are a group of compounds that contain an alkyl group, carbon and hydrogen chain, bonded to a halogen, fluorine, chlorine, bromine or iodine. In simple terms, they are like an alkane where a halogen has taken the place of a hydrogen. Nitriles are a group of compounds that contain a CN group, in which a carbon atom has a triple bond to a nitrogen atom. Apart from with iodine, the carbon-halogen bond in a halogenalkane is polar due to the halogen's high electronegativity and carbon's low electronegativity. This means the halogen pulls the electrons in the bond towards itself slightly and, as a result, has a partial negative charge. And the carbon it is bonded to has a partial positive charge. As halogen size increases down group 7 in the periodic table, from fluorine to iodine, the covalent bonds they make to carbon get longer and therefore weaker. This means a carbon-fluorine bond is very strong and has a very low reactivity. A carbon-iodine bond, however, is weaker and more easily broken, making iodoalkanes much more reactive. A nucleophile is an electron-paired donor that is attracted to a positively charged or electron-deficient atom. Nucleophiles can be negatively charged and always have a lone pair of electrons. A substitution reaction is where one group or atom in a molecule is swapped for another group. In organic chemistry, we showed the possible steps occurring in a reaction by using mechanisms. Curly arrows are used to show how a pair of electrons move as bonds get broken and formed. The arrowheads always point towards where the electron pair is moving to. Recap done? Let's go! Halogenalkanes can react with cyanide ions in ethanol to form a nitrile. The reaction is an example of nucleophilic substitution. Heat is needed, and to prevent the escape of volatile reactants from the reaction mixture, reflux conditions are used. A cyanide ion is made up of a carbon atom and nitrogen atom held together by a triple bond. The carbon atom has a lone pair of electrons and a negative charge. This means it is able to act as a nucleophile. A good source of cyanide ions for reactions is potassium cyanide, as it is highly soluble in both water and ethanol. And, when dissolved, the potassium ions don't interfere with reactions and remain as spectator ions. The carbon atom bonded to a halogen in a halogenalkane has a partial positive charge, and this makes it vulnerable to attack by nucleophiles, often called nucleophilic attack. When a halogenalkane is mixed with cyanide ions, the carbon in the cyanide ion gets attracted to this partially positive carbon and uses its lone pair of electrons to form a bond to it. At the same time, the carbon-halogen bond will break, with the bonding electron pair going to the halogen, forming a halide ion. The original halogenalkane has become a nitrile. The released halide ion can pair up with the positively charged potassium ion from the original potassium cyanide and form a potassium halide salt. During the reaction, there is a very brief period of time where the incoming cyanide ion and the outgoing halide ion are both attached to the central carbon. This structure is referred to as a transition state and is too short-lived and unstable to ever be isolated. The species starts in the reaction, the cyanide ion acts as a nucleophile, making the reaction nucleophilic, and the CN nitrile group has been substituted for the halogen in the molecule, making the reaction substitution. This is why the reaction mechanism is described as nucleophilic substitution. There are actually two ways this reaction can occur, depending on the type of halogenoalkane reacting, and these are referred to as SN1 and SN2 reaction pathways. The examples shown in this video are SN2 as primary halogenoalkanes are used. If a tertiary halogenoalkane was undergoing substitution with a cyanide ion, an SN1 mechanism would occur where the carbon-halogen bond has to break before the nucleophile, cyanide ion, can form a bond to the carbon. SN1 and SN2 mechanisms have been covered fully in a separate video. Check the links in the description below. As an extra note, if the reaction is carried out in water, aqueous conditions, rather than in ethanol, ethanolic conditions, a hydrolysis reaction can occur and an alcohol formed instead. Again, this has been covered in a separate video. Check the links in the description below. Let's have a quick recap of this reaction and mechanism using bromoethane and potassium cyanide as an example. Potassium cyanide is dissolved in ethanol and dissociates, splits apart, and is mixed with the bromoethane. The reaction mixture is heated under reflux. The negatively charged carbon in a cyanide ion is attracted to the partially positively charged carbon from the carbon-bromine bond and uses its lone pair of electrons to form a bond to it. At the same time, the carbon-bromine bond breaks and the bonding pair of electrons goes to the bromine, forming a negatively charged bromide ion. A nitrile, propane nitrile, is produced. Propane because the product has 3 carbons in its longest carbon chain, and nitrile because it has a CN nitrile functional group. Potassium bromide would also be present as a product due to the negatively charged bromide ion released in the reaction and the positively charged potassium ion that came from the potassium cyanide reactant. The formation of nitriles using cyanide ions is really important in organic chemistry, as these reactions form a carbon-carbon bond. This enables us to make a carbon chain longer and, with further reactions of the nitrile group, can add other groups to a molecule. In our example with bromoethane, propane nitrile was formed. The carbon backbone went from 2 carbons, ethane, to 3 carbons, propane. This makes it a very important reaction for multi-step synthesis-based exam questions. In these substitution reactions, the carbon-halogen bond must break before the nitrile can be made. The easier it is to break the carbon-halogen bond, the faster the nitrile can be formed. Due to the size of the halogen atoms increasing, carbon-halogen bond length increases as you go down group 7 in the periodic table, and this makes the bonds weaker. Meaning carbon-fluorine bonds are the strongest and carbon-iodine bonds are the weakest. As a result, iodoalkanes will react more quickly than bromoalkanes, and bromoalkanes will react faster than chloroalkanes. Carbon-fluorine bonds are so strong that fluoroalkanes won't react at all. So, to summarize, halogenoalkanes can react with cyanide ions in nucleophilic substitution reactions to form nitriles. The reaction must be carried out in ethanol, ethanolic conditions. No water can be present to stop an alcohol from forming. Reactants are heated under reflux, and a common source of cyanide ions is potassium cyanide. The reaction is an example of nucleophilic substitution because the carbon in a cyanide ion has a lone pair of electrons and acts as a nucleophile, using this lone pair of electrons to bond to the partially positive carbon atom in a carbon-halogen bond. As the carbon from the cyanide ion forms this bond, the carbon-halogen bond breaks, with the bonding electrons going to the halogen, forming a halide ion. A transition state occurs with the incoming cyanide ion and outgoing halide both attached to the carbon at the same time. This is more specifically referred to as an SN2 mechanism and occurs when primary and secondary halogenoalkanes react. For tertiary and some secondary halogenoalkanes, a different mechanism pathway referred to as SN1 occurs, where the carbon-halogen bond must break before the cyanide ion can make a new bond to the carbon. A potassium halide salt will be produced in both of these types of reactions, formed from the positively charged potassium ions from the original potassium cyanide and the negatively charged halide ion released in the reaction. The rate of reaction is determined by the strength of carbon-halogen bond in the original halogenoalkane. As halogen atoms get larger as you go down group 7 in the periodic table, the carbon-halogen bonds get longer. This makes the carbon-halogen bond weaker, and as a result, it can react faster. Carbon-fluorine bonds are too strong to break in these nucleophilic substitution reactions, making fluoroalkanes unreactive. Iodine carbon bonds are weaker than bromine carbon bonds, and bromine carbon bonds are weaker than chlorine carbon bonds. As a result, iodoalkanes react fastest and chloroalkanes react slowest. I hope you found this video useful. Please check out other relevant videos in the links given in the description below, and visit chemistrystudent.com for free notes and revision materials.